All right, congratulations. This is it. This is our last section of the course. The very last thing we're going to be talking about is the divergence theorem. And the divergence theorem is really just another extension of Green's theorem. The divergence theorem is actually an extension of the flux form of Green's theorem. So Green's theorem, when we said when we're computing flux of a vector field, we can change this line integral as an area integral of the divergence. And so we kind of did that at the very end of our Green's theorem chapter. Again, at the bottom of the screen, there's our two-dimensional version of Green's theorem, or I should say the flux form of Green's theorem. In 3 dimensions, what this becomes is if we have a solid region that's bounded by a closed surface. So imagine something like a sphere or maybe a box, any type of closed surface that's creating a volume or a solid region. We're going to orient those surfaces outward. So normal vectors always pointing out from the surface. This is saying then that the flux across those surfaces, so our f dot n ds, our surface integral, is going to be equal to the divergence of our vector field integrated over the volume of that region. And so once again, just like I did in the last section, to show you how this works, I'm going to do an example 2 different ways. I'm going to compute the following problem. I'm going to find the following problem by computing surface integrals and then a volume integral. So the left side and the right side of our divergence theorem, and hopefully we will get the same answer. So we are going to verify the divergence theorem for the following vector field. We've got the vector field 3x, 5y, 6z, and S, our surface, is bounded by the coordinate planes, so like our xy, xz plane, etc., and the plane 2x plus y plus z equals 4. So I'm going to go ahead and graph the region we're talking about. So we've got this plane 2x plus y plus z equals 4, and we're really, since we're bounded by the coordinate planes, we're just looking at the piece of this that's in the first octant. So we've got this kind of triangular solid that we're considering. And so we're going to start with part A. We are going to compute surface integrals of this vector function. And for this region that we're looking at, technically we actually have 4 surfaces we have to consider. So again, we're thinking about a volume, a solid volume, and all of the surfaces around that solid volume. So surface 1, for example, is what I have shaded in purple. That's actually the plane z equals 0. That would be the plane z equals 0. And we want all of our normal vectors to point outward from this object, this volume. And so since that z equals 0 is on the bottom of my object, my normal vector would have to point down. So my normal vector would be 0, 0, and then -1 pointing down. The second surface we're going to consider would be, I guess that's, what is that, my xz plane. So that is the plane y equals 0. And again, I want my normal vector to point away from the surface. I want it to point outward. So my normal vector for that surface would be 0, -1, 0. My third surface is the plane x equals 0. Again, that normal vector is pointing outward, so -1, 0, 1. And then finally, the fourth surface we're going to consider is actually that slanted plane. It's the plane 2x plus y plus z equals 4. And my normal vector there would be 2, 1, 1. I got that very quickly by just looking at the coefficients of the plane. That's definitely my normal vector. I guess if you want to connect this to how we've been finding our surface integrals in the past, in this case, we could say that our g of x, y is the equation for, no, solve it for z. Z equals 4 minus 2x minus y. Our g sub x is negative 2. Our g sub y is negative 1. So our normal vector is negative g sub x, negative g sub y, comma 1. Oh, and that does give me positive 2, positive 1, comma 1. All right, I'm going to erase all this. Kind of messy. All right, so I have got 4 surface integrals I'm going to have to compute. Fortunately, I think some of these are going to be faster than the others. So we'll do one at a time. We'll start with surface 1, which is the plane z equals 0. So if I take my vector field dotted with my normal vector, f dot n, I end up getting, let's see, where is my vector field? It's up here. Let me circle it. So I get 0 times 3x plus 0 times 5y plus negative 1 times 6z. I end up getting negative 6z. But then, if I plug the equation of my surface into that expression, my surface is always z equals 0. So I end up getting negative 6 times 0, which is just 0, and this integral is going to turn into 0. So you integrate 0, you get 0. Something similar happens with surface 2. We have the plane y equals 0. So I'm on surface 2 now. And so if I take my vector field dotted with that normal vector, I get 0 minus 5y plus 0, so I get negative 5y. But once again, notice our surface was y equals 0. And so if you plug that in, once again, you're just integrating 0, which gives you an answer of 0. All right, and guess what? Same thing happens with surface 3. We have the plane x equals 0. We take f dotted with n. We get negative 3x, but on this surface, x is always 0, and so when we integrate 0, we get 0. Okay, so those first 3 surfaces, those coordinate planes, just gave me answers of 0. Let's see what happens with our 4th surface. Our 4th surface is actually that plane, z equals 4 minus 2x minus 2y. And now when I take my vector field dotted with my normal vector, dotted with that negative gx, negative gy, comma 1, so f dotted with n, now I get 6x plus 5y plus 6z. And so that's what I'm going to actually integrate. So we are going to integrate f dot n, and I am going to go ahead and plug in the z for my surface. So I'm going to plug 4 minus 2x minus y in for z. So now I got that big expression, 6x plus 5y plus 6 times that plane. And then I am going to be integrating this over its projection in the xy plane. So in my picture, I shaded in blue the projection of that surface in the xy plane. I did something else. I also distributed the 6 combined like terms, and I ended up getting the quantity 24 minus 6x minus y. And so that's what I'm going to integrate over that region that I have shaded in blue, which is the projection of my surface over the xy plane. So in that particular region, the y values are going to go from y equals 0 up to this line, y equals minus 2x plus 4. Here it is. There's my plane. I just plugged in 0 for z, and that's how I got that y equals 4 minus 2x. Okay, so the y values go from 0 to that line, 4 minus 2x, And then the x values go from 0 to 2. 0 to 2. So I'm going to start with my inside integral. Integrate with respect to y. I got 24y minus 6xy minus 1/2 y squared. Plug in my bounds of integration. So I'm going to have to plug in that 4 minus 2x in for all the y's. I erased some stuff to make some more room. So I plugged in that 4 minus 2x in for all the y's. You could probably do some clever factoring. I feel like you probably could. I don't know. This time I decided to just go ahead, use some brute force, do some multiplying. So I distributed, I FOILed out the 4 minus 2x squared, did some more distributing, combined like terms, and I ended up with, it's at the bottom of the screen, 10x squared minus 64x plus 88. So to finish, I'm going to integrate that quantity with respect to x. That gave me 10x to the third over 3 minus 64x squared over 2 plus 88x. And then I plugged in my bounds of integration, so plugged in 2, plugged in 0. I used a calculator to finish this one up and got a final answer of 224 over 3. Hopefully I didn't make any mistakes in my calculator. I didn't write it out. But there's my answer, 224 over 3. All right, so we have completed part A of this problem. Technically what we've done is we have computed 4 surface integrals of each of the surfaces that are bounding this object. So we have computed 4 surface integrals. And what the divergence theorem tells me is that this answer I got should be the exact same answer if I compute the divergence, or I integrate the divergence of this vector field throughout that volume that I have drawn. And so let's do that next. We've got this volume. Let's compute the volume integral of our divergence. So I'm going to find the divergence of my vector field, which is del dot f. So I have to find derivative of 3x with respect to x plus derivative of 5y with respect to y plus derivative of 6z with respect to z. Let's see, I got, 3 plus 5 plus 6. That's 14. So that's nice. My divergence is relatively simple. It's just 14. So I'm going to be integrating 14 over the volume of the region drawn. So I think I'll do the z's first. So in this region, the z values always start at 0, and they stop at that plane. So they start at 0, and they stop at the plane z equals 4 minus 2x minus y. And then to get the y's and the x's, I'm going to think about the projection of this plane in the xy plane. So I'm looking at that blue little triangle. The y's are going to go from 0 to y equals 4 minus 2x, and the x's go from 0 to 2. All right, so we'll solve this integral. Inside integral, I get 14z, plug in my bound of integrations, and I get 14 times 4 minus 2x minus 2y. I think I said that wrong. 14 times that plane, which was 4 minus 2x minus y. I distributed the 14, so that's how I got the 56 minus 28x minus 14y. All right, second integral. Now I'm going to integrate that answer with respect to y, and then I'll plug in my y bounds of integration. So antiderivative would be the 56y minus 28xy minus 7y squared. I plugged in the 4 minus 2x. And then I'm going to go ahead, there we go. So antiderivative, I plugged in the 4 minus 2x in for the y's. And then I did lots of algebra. So I distributed, did some foiling, more distributing, combining like terms. And I was left with that 28x squared minus 112x plus 112. All right, that was the second integral. So then to finish, I'm going to integrate this answer with respect to x. And there we go. So on the bottom of the screen, I'm going to integrate my answer with respect to x. I had to erase to make a little bit more room. There's my antiderivative, 28x to the third over 3 minus 112x squared over 2 plus 112x. Finally, almost done. Plug in those bounds of integration. Plug in the 2, plug in the 0. I once again used a calculator to help me. And there it is. Final answer is 224 over 3. So I got the exact same answer I got in part A, which is good. That's exactly what should have happened in this problem. Okay, so again, what the divergence theorem is telling us is that if we want to integrate a vector field over a closed surface, we can integrate the divergence of that vector field over the volume, and that will give us the exact same answer. So let's do, I think I have 2 more examples. So I have a different vector field. So my vector field is written on the screen, and the surface is z equals 1/2 square root of x squared plus y squared, and then also bounded by the plane z equals 8. We are going to find the outward flux of F through S. And that is essentially what we're doing. When we're computing these integrals, we are actually finding flux. So we're going to compute the flux of F through this surface S. So first of all, the surface that we're talking about, that z equals 1/2 square root of x squared plus y squared, that's a cone. So we have this cone, and it's topped at z equals 8, topped by that plane z equals 8. So we're finding the flux, outward flux through both the cone and then the top of that cone. And so what the divergence theorem tells us is we can actually integrate the divergence of our vector field through the volume of the image, the region graphed on the screen. And in most cases, I think the volume integral is easier than the surface integral, but it does depend. But most of the time, I prefer to do the volume integral rather than the surface integral. So we are going to first compute our divergence. So what is the divergence of our vector field? So I'm going to find the derivative of xy squared plus cosine z with respect to x. And then I'll find the derivative of our y component with respect to y. And the third, or the z component, with respect to z. So I went ahead and computed the divergence, and I got, let's see, y squared, and then the derivative of x squared y plus sine z with respect to y is just x squared. And then finally, derivative of z with respect to z is 1. So my divergence is y squared plus x squared plus 1. So that is the quantity we're going to integrate, and we're going to integrate that quantity over the cone that's graphed on the screen. Now, we are dealing with this cone, and so I actually think this integral is going to be a little bit easier in cylindrical coordinates. So there's circles involved, so putting this into polar or cylindrical coordinates I think makes the most sense. Okay, so there's the volume integral I'm computing. Again, I'm going to convert this into cylindrical coordinates because that cone, z equals 1/2 square root x squared plus y squared, actually turns into z equals 1/2 times r. So the equation gets much simpler in cylindrical coordinates. So my integral in cylindrical coordinates, let's see, the y squared plus x squared is an r squared. So the function I'm integrating becomes r squared plus 1. And then I'm going to replace the dv with the r, dz, dr, d theta. heights, the z-values, start at this cone and stop at the plane z equals 8. So lower bound, they start at the cone, which is z equals 1/2 r, and they stop at the plane z equals 8. So those are my z values. And then for my r values, as well as the theta values, you can think about the projection of this object in the xy plane. So in the xy plane, the shadow of this object really comes from the top of the cone. If my cone is z equals 1/2 r, it intersects the plane z equals 8 when 1/2 r equals 8 times by 2, so when r equals 16. So the projection or the shadow of this object is actually going to be a circle with a radius of 16. So my r values are going to go from 0 to 16, and then we're going all the way around the circle, so thetas are 0 to 2 pi. So I'm going to start by finding my inside integral, and I did go ahead and distribute that extra r. So r to the third plus r, I'm going to integrate that with respect to z. So I got r to the third z plus rz. And then I'm going to plug in my bounds of integration and subtract. So I plugged in 8 for z, and then I plugged in the 1/2 r for the z's. There weren't really any like terms. Wasn't much to do. I just rewrote it in a different order. But plugged in the 8's, plugged in the 1/2 r's, subtracted. And now I'm going to integrate that result, which was negative 1/2 r to the fourth plus 8r to the third minus 1/2 r squared plus 8r. We're going to integrate that with respect to r. So I have my antiderivative on the screen. Negative 1/10 r to the fifth plus 2r to the fourth minus 1/6 r to the third plus 4r squared. And then I definitely used a calculator to plug in those bounds of integration. I had to go ahead and plug 16 in for those r's. I put it into my calculator. Hopefully didn't press any incorrect buttons. Got that kind of big, ugly number on the screen. What is that? 796,672 divided by 30. So then I took that result, integrated it with respect to theta, plugged in the 2 pi, plugged in the 0, and my final answer, it's a little ugly, it's on the screen, that's 796,672 pi over 15. There we go, and that is my outward flux of my vector field through the surface that was described. All right, I think I put one more example in here just because. There we go, one more example. So same thing, different equations. We're going to find our flux of our vector field, which is 3x minus y plus z squared, through S, where the surface that we're considering is the hemisphere given. So we're thinking about half of a sphere, the top half of a sphere, and this would be a sphere with a radius of 3. So hemisphere, radius of 3. So first thing I have to do is compute my divergence. So del dot f, derivative of my x component with respect to x was 3. Derivative of my y component with respect to y is negative 1. And finally, derivative of the z component with respect to z is 2z. So divergence simplifies down to 2 plus 2z. So the divergence theorem says we can integrate 2 plus 2z. We can integrate that quantity through the volume of this hemisphere. Since we're talking about a sphere, this seems like a really good candidate for spherical coordinates. And so I'm going to convert this integral into spherical coordinates. I just jotted down all those relationships for spherical coordinates, just in case you've forgotten them. I think, though, this case, what do we need to use? I don't think we need to use all these formulas. We just need to replace the z with rho cosine phi. And then I'm going to replace my dv with rho squared sine phi d rho, d phi, d theta. Okay, so went ahead and did that, plugged rho cosine phi in for my z, and then plugged in that rho squared sine phi d rho, d phi, d theta for the dv. All right, so then let's get our bounds of integration. The radiuses of this sphere, the radius of the sphere is always 3. So the region I'm looking at has radiuses or rho values from 0 to 3. And then phi is angles made from the positive z-axis. So starting at 0, and since we're only talking about half of a sphere, we're going to stop when we get to that xy plane. So we only go down 90 degrees. So my phis go from 0 to pi over 2. And then we're going all the way around the circle, so the thetas go from 0 to 2 pi. So the great thing about spherical coordinates is all my bounds of integration are constants. So that's kind of nice. And so now I just have to integrate everything. I'll start with integrating with respect to rho. And I went ahead and distributed that rho squared sine phi. And then I can integrate with respect to rho. I ended up getting, let's see, we got a 2 rho to the 3rd over 3 sine phi plus 2 rho to the 4th over 4 sine phi cosine phi. Plug in my bounds of integration, the 3 and the 0, and that simplified down to 18 sine phi plus 81 over 2 sine phi cosine phi. So next integral, we're going to integrate that result with respect to phi. So I got negative 18 cosine phi. And then for that sine phi, cosine phi, I technically I'm doing a u sub there, letting u equal sine phi. Du is cosine phi, d phi. So you integrate, you get like a u squared over 2. So that turned into the 81 over 4 sine phi squared. Plug in those bounds of integration, so I plugged in pi over 2. Plugging in pi over 2 gave me the 0 and then the plus 81 over 4. And then I plugged in 0, negative 18 plus 0, subtracted them, ended up with 153 over 4. All right, one more last piece. We're going to integrate that 153 over 4 with respect to theta, plug in the bounds of integration, and there is my final answer, 153 pi over 2. Right, so main idea here is we can integrate the divergence of a vector field throughout a volume, and that's going to give us the same answer as if we were to integrate the flux of that vector field through that closed surface. All right, so that was it. Last example, last video. As always, let me know if anything was unclear in this video.